Hey everyone, this is the notes and examples that we're going to do for the factor theorem, which is the second of the two sets of notes inside that little booklet on notebook page 65. If you are in second or third period honors today, which was Monday, January 30th, then you already got these notes today. But if you need a review, or if you were not in those classes today, or if you're in my sixth period honors, I was not there because I went to the doctor again, then you're definitely going to need to watch this video in its entirety. It might be split up into parts 1 and 2 because it's a pretty big topic. It's a little bit bigger than remainder theorem. So also, if you're a CP class student, first period or fifth period, you have not seen this ever. Again, this is in the booklet where we just took notes on the remainder theorem. It's the page right beside it to the right, same booklet called Factor Theorem. Okay, so there are a couple things I want to review with you before we get into the factor theorem, because the factor theorem and the remainder theorem are kind of similar, but we use them for different things. We need them for different reasons. Okay, so the first kind of backstory we want to do is the factor theorem warm-up. Part 1 here is to determine whether 8 is a factor of this really big number, 8,576. So here's what we do. First of all, just to kind of review what factors are. Factors are the numbers that would multiply to give you a bigger number. So I'm going to start with something small like 12. The factors of 12 would be like 1 times 12, 2 times 6, 3 times 4, and then of course 6 would be the next one, but we've already got 6 here. It'd be 6 times 2. So we've got them all when we start repeating ourselves. So 1, 2, 3, 4, 6, 12. These are the factors of 12. So if I want to take the big number, 12, and if I want to divide it by, I don't know, 4, I'm going to get the answer 3, right? Because 4 is a factor. It's going to go in evenly 12 times with no remainder. Okay, if I do it again, let's say this time I want to divide by 6. Well, 6 is a factor of 12, so it's going to go in evenly 2 times for 12, and what do you know? There's no remainder. Any factor that I use here, let's say I used 12, it would go in 1 time evenly with, you guessed it, no remainder. So what can we say about the relationship of these factors, right, and the actual number that they are factors for? Okay, well, we can say, this is the multiple, by the way, we can say that factors go evenly into the multiple with no remainders. Okay, so now let's take that concept and apply it here. If 8 is a factor, then it will evenly go into this larger number with, yep, no remainders. So we would just have to check it out. We would actually have to divide and see if it goes in evenly or not. Okay, so it'll go in once here for 8, 0, bring down. Remember, dirty monkeys smell bad. Okay, that'll go in 0 times. So I'll subtract and bring down. 7 times 8 is 56. There'd be 1 left over after I subtract, and now I bring down and I have 16. And I think you know the rest. We're going to have a 2 here. It's going to have 16, and you guessed it, no remainder. So what does this mean when a number will go evenly into a larger number with no remainders, then we say this number is a factor. Yay, that means it could be multiplied evenly with no remainders to get the larger number. Okay, that's going to be pretty important coming up in the factor theorem. It's like kind of the basis of the whole thing, actually. The other thing is, when we start to use the factor theorem, we are going to end up using it to break down larger polynomials. So we're going to have a polynomial. Most of the time they're going to be like the highest degree will be a 3. So it'll be something x to the third. It'll be a big polynomial. And they're going to want us to use the factor theorem. And I'll teach you how to do all this, but they'll want you to use it to actually, they're going to want you to use it and actually find, oops, what happened to my screen? Sorry. They're going to want you to use it and actually find how to break it down more and more. And the only way you're going to break it down evenly is with an actual factor. What would happen here if I picked a big number like this 8,576, and let's say I picked 5. And I said I'm going to break it down with 5. I think you already know it's not going to work, but okay. When I do that, I'm going to get a 7, 0, bring down a 7, I'm going to get 1, 2 left over, 26, 5, 25, and a remainder of 1. So now, if I tried to divide this new number, this smaller version, and break it down again by something else, that's going to be really hard to do because it's got a remainder 1 or 1, you could say 1, 7, 1, 5, and 1/5. Excuse me, so I've just made my job of continuing to break this down a lot harder. Whereas when I used 8, I got a nice whole number here. So if I wanted to break this down again and I chose a number that actually worked, like was a real factor, then I could divide it again and it would work out beautifully. Okay, like a 2 or something along those lines. And I could continue breaking it down. There's nothing, now, since I used a non-factor 5 and tried to break it down, when I try to break it down again with this new smaller number up here, it's really complicated because we have a remainder. So when we are depressing and breaking down polynomials, we want to divide them by true factors so that what we have left over is then depressible again, or we can break it down again. If we divide by something that's not a real factor, it will not break down nicely the first time, and then that kind of screws you up for all the future times that you could have possibly broken it down. Okay, so that's the purpose of the factor theorem. I'm going to teach you how to use it in a minute. But speaking of, and you don't have to do this part, just ignore that. Speaking of breaking things down, if you depress a third-degree polynomial, then your result, your new polynomial after you break it down, is going to be an x squared. And so how do we typically break down quadratics? Well, I know that the quadratic formula will work at all times, but the one that is favored above all, when possible, would be this, which is just factoring a quadratic equation. So we know that to get x squared out of these first two terms being multiplied, or FOILed, some of you call it, but basically distributed property here, to give us the x squared here, we would need x times x. All right, now to get these next two terms, I have negative, which means my signs are opposite. To multiply a positive times a negative. So I'm going to make that one a plus and that one a minus. I know my signs are opposite because that's a negative. Now, how would I get a 15 with multiplication? Okay, well, I could do 1 times 15, or I could do 3 times 5. There really aren't a lot of other options here. Now, remember that I've got to multiply to 15, but I also have to add or subtract to get this middle term, 2, right here. Positive 2 at that. With addition or subtraction, I need to multiply to 15, but whichever one of these I choose also has to add or subtract to give me 2. I think it's pretty obvious we're going to use a 3 and a 5. Okay, the 2 needs to be positive, so the bigger number needs to be positive here. So that 5 is going to be the positive. So the 5 is going to be the positive, or the plus. The 3 will be the minus. All right, and that is how you factor a quadratic equation or function. And that's actually how we'll do it. We're going to find a factor, determine if it's a factor or not, and then break it down, depress the third degree polynomial. So we'll have a little polynomial, like a binomial actually, that we use to divide by, and then we'll have this quadratic, and then we'll break him down even further. And when we're done, we'll have all these, and these things in parentheses are called factors. Okay, these will be the factors. Now, it's also going to ask you to take it one step further and name the roots or the solutions, and you know they're also called zeros as well. And how do we do that? Just a quick review. We set each factor equal to 0. And then you solve for x, like that. And is going to be a -5 and a 3. So remember, these guys right here are called factors. They're on the same side as the x. There's no equal sign inside there anywhere. These guys, these roots or solutions, are going to be set x equals. They're going to say x equals something. And remember, these roots or solutions is where the graph will cross over or touch the x-axis. So they have to be set x equals. Those are the roots or solutions. Don't get them confused. They're going to ask you for both of those along the way. Okay, so we're going to get started, and I know we're going to get interrupted, and it'll have to do a part 2 here. But in this foldable from 65 that you should have just taken notes on, if you open it, on the right-hand page should be notes that look like this. Okay, yours are not going to have the blue squiggly lines. I just did a screenshot out of Microsoft Word, and it, had grammar check or something. So disregard that. We're going to get as far as we can before we have to stop and switch. My time will run out. Okay, so just walking you through what it looks like. So we said that the factor theorem is just a quick way to tell if something has a 0 remainder or not, which means it's a factor. This is the fancy language. If you have a polynomial and it's called f of x, and if it has a factor, x plus or minus anything here, it's a factor if and only if f at that k value, substitution here, equals 0. Now that looks almost like the remainder theorem, right? It said something similar. The remainder theorem said is f at k would equal your remainder. Remember, so whatever you get is your remainder. The factor theorem is similar but different. It says if you solve for, set this equal to 0 and solve, then whatever you're using as this value, if you plug it in and it equals 0, then this guy, or this original guy here in parentheses, was a factor. If it equals anything else, it's not a factor. Very similar to when we divided by 8 in the original problem, right? If it doesn't have a remainder, it is a factor. If it has a remainder, like the 5 did, 5 was not a factor. So this is all about testing the remainders, okay? So follow along here. These are already done for you, but basically, they want to know if x minus 3 is a factor of this big polynomial. So of course they set this equal to 0, so x would equal 3. And they want to prove to you that f at 3 equals 0. That means if they plug in a 3 everywhere, the result will be 0. You can test that out on your own in the calculator, and in fact it does equal 0. So what that means is the factor theorem can prove really quickly that all of that equaled 0, and since the remainder equaled 0, so then x minus 3 is an actual factor. It is a factor. That's what it means. And that'll just tell you that that's something you can use when you are going to go depressing the polynomial. It'll tell you that this is going to be legit. It'll break down nicely, and then you can go on and proceed to continue breaking it down again. You won't have any messy remainders. Okay, so my time's almost up. I'm going to stop the video. We're going to do examples 2 and 3 in these notes, and then we're going to do a whole nother sample page of notes, another 3 or 4 questions before I give you homework. So I'll see you on part 2.